my name is Jo Franchetti and I am a developer advocate at Ably. And Ably provides the infrastructure and tech that developers need to use real-time data to build apps. And as a developer advocate at Ably, I get to make all kinds of fun projects. And I particularly like to make wearable technology, specifically things with lots of lights in that I can connect to the internet because I like to be sparkly. And I started making wearable tech projects a couple of years ago, my first being a light-up tweet-controlled wedding dress. And when I started, I had no real clue what I was doing, and I made quite a few very silly mistakes around choices of hardware and how to stick it all together. And so my hope for this talk is to give you a little bit of a direction for those of you who are thinking about starting a hardware project and to help you get over that initial hardware is scary hurdle. And this time I wanted to make something that all of you could interact with, that we could all use together, because I don't know about you, but I've been missing having friends and colleagues and just other humans around me recently. So I thought, what if I made a wearable that lets my friends change the color of what I'm wearing in real time? I'd be able to see the changes they were making as they happened, kind of like a multiplayer version of MS Paint, but wearable. So in order to realize this dream, first we're going to need a few things. We need an array of lights that we can change the color of. We're going to need a microprocessor to control those lights. We're going to need an app where our users can change the color of the lights. And we're going to need a method of sending messages to and from the app to the microprocessor. So let's start with the array of lights. So I decided to make a 16 by 16 grid of LEDs. And the LEDs that I used in this project are called addressable RGB LEDs. Addressable means that we can target each one individually. And RGB means that we can set it to basically any color you can think of, using a similar color value to that which you're used to from your CSS. So if you've seen the RGB 3 values in brackets, that's exactly the same thing that we're setting on the LEDs. And the product name for this is NeoPixels. If you're looking to buy them, that's what you want to look up. And they come in these ribbon strips, which makes working with them nice and easy because we don't have to individually solder each LED. It also makes them nicely robust for a wearable because we've got fewer solder points, which means fewer points where it could potentially snap while you're wearing it. And these strips are great because they have clear labeling for which lines carry power, which carry data, and which are the ground. You can see them there. So DI is our data, 5 plus V is our power, and the minus is our ground, which means that you're much less likely to make a mistake when you're connecting them up. And to keep the strips safe in a wearable, what I decided to do was I sewed 2 pieces of fabric together to make long pockets to insert each strip into. So that is visualized here. And this is what it actually looked like with my very messy sewing shown here in a photograph. And then once the strips are inserted into each pocket, they need to be soldered together so that we have a complete line going through each one. We need to connect up the data to the data, the ground to the ground, and the power to the power. You can buy a soldering iron and solder from about £30 online. And here I used, you can see here, this is single core copper wire, which is nice and easy to solder because the ends don't fray. I recommend also getting one of these, which is a heat-proof silicone mat, which you can put on your desk while you're soldering, which means you're not going to burn through your desk. They also double up as really great cookie sheets for baking. So if you're making cookies, also recommend one of these. And there's lots of tutorial videos for soldering online, so I won't go into it here. Suffice to say that it isn't too scary. And once you've had a few goes at practicing, you'll get the hang of it very quickly. So once both ends are both soldered up, we have a finished flexible LED array, which we can put into a wearable. And it looks like this. I hope that video is playing for all of you, but hopefully you can see that it's pretty strong, it's pretty flexible, and that makes it nice and durable for our wearables. So now we need to be able to control what color we're sending to the LEDs. And for that, I'm going to use a microprocessor, which is great because they can do enough calculations to control the lights, but they're nice and small, so they can be easily hidden in a wearable. So I opted for this one, which is the Adafruit Feather Huzzah, and I like it because it's super small. I've got one here. Let's see if I can hold it up to the camera. You can see how tiny that is, which means that it is very easily hidden in a wearable. It's just 5 centimeters by 2 centimeters, and it has Wi-Fi on the board, which means that I can connect it to the internet directly. I don't need to attach any other Wi-Fi chips onto it. It's not too expensive. It's about £25 to buy online, and it's low power, which means that it can take either USB power from a USB charger or from a battery, or from something like the battery in your phone. And they run C and C++ out of the box. You write software for it using the Arduino IDE, which you can download for free online. And the Arduino IDE is really great because it comes with loads of libraries and a whole bunch of example code to get you up and running with the board quickly, especially if, like me, you haven't written much C or C++ before. So the code for the Huzzah looks a little bit like this. So here, I hope you can see what I've done is I have first of all included the NeoPixel library, which is what we're going to need in order to drive the lights. I've told it how many lights I have connected, which is this numLights variable here, which is 265. I've told it what pin I'm going to be sending the data out on, so that's pin number 4. And in fact, I have a little diagram here so you can see where pin number 4 is. And so what I'm doing here is firstly, I'm initializing the strip, which makes it possible for us to send colors to it, but it sets all of the LEDs off initially. We're then going to loop through each LED, which is what we're doing in this loop here. And we're using set pixel color to set the color of all of the pixels. So we're looping through 265 times to set the pixel color to 255, 255, 255, which is white. So what this loop will do is set every single pixel in the array to white. So the next thing I need to do is to connect my board up to my array. So I'll be connecting pin 4 to the data line. I'll be connecting this USB power shown here to my power line, and I'll be connecting ground up to ground. And then the board itself is charged by a USB battery, which comes out through the USB battery connector down at the bottom. So now we have a display and we have a way of controlling it. We need a way to tell the controllers what colors to set. And being a web developer, I opted to build a web app. And you can check out the code in my web app here. It's on Glitch at Ably MQTT-IoTshirt. Don't worry, I will share these links out on Discord, and I'll share the slides out as well later, so you can check the code out at your leisure. And the app looks like this. It has some buttons at the top where the user can pick a color, and it has an SVG of squares underneath, and each square has its own number. So 0, 1, 2, 3, 4, so on and so forth. And once a color and a square has been selected by the user, the app updates to fill the color of that square to match the selected color. I see somebody's on the app already. But what we want to do is we want to also not only light up the correct color on the app, but also on the t-shirt. And we can do that using a real-time data service to create a channel on which we're going to publish messages that contain the color updates. We can also subscribe to this channel to listen for changes made by other people who are also using the web app. So if you haven't already got there, you can go and have a go of the app at ably-mqtt-iotshirt.glitch.me. And we'll send that out later as well. So what have I actually done here? So on the front end, I used Ably's messaging platform to set me up with a channel. And then I used their JavaScript SDK to manage the publishing and subscribing to messages on this channel. So here, what we're doing is we're making a new instance of the Ably real-time library. Then we're connecting, well, we're creating a channel called T-shirt, and we're connecting to that channel, and then we're subscribing to it to get the messages. The cool thing is that every single user of this app is also subscribed to these messages, so their clients will update when other people paint cooperatively with them. And then on the back end, I'm using Ably's SDK to create a token request, which is what is going to allow me to authenticate. I do this instead of sending the API key directly, just because it's slightly more secure. It keeps the API key nice and safe. As an aside, all of this code is on GitHub as well, and I will share the link to the GitHub out at the end, and you can have a look. You can create your own t-shirt. So now that we've established a connection to a channel, we need to publish a message to that channel when someone clicks on a square. So what I've done here is I've set an event listener on square, and when clicked, it's going to get the number of that square. It's going to change the fill of the square on the SVG. And for those of you who haven't used SVGs before, fill is just the same as background color. And then it'll publish both the square number and the color value that was selected to our t-shirt channel, which is happening here, channel.publish. So let's look at an example of what is possibly being sent. Say we sent pixel number 1 to be purple. When I click on pixel number 1 and set it to purple, this is what is going to be sent on my channel. But I want the web app to also display the pixels that are clicked by other users. So I need to not only publish, I need to also subscribe to that channel. And the updated pixel values are what we're going to get on that channel. I've also got here an option for a reset in case anybody manages to draw anything not safe for work on 16 by 16 pixels. So what I've got here, I will either receive a single pixel message or a reset display message, depending on if I want to reset. Now this is all well and good, but I also need a way to get the data from the app to the Feather Huzzah. So you might, I imagine you are familiar with HTTP, the protocol that browsers use to request web pages. And HTTP is a protocol, and the word protocol just means that it's the way that two things talk to each other. And HTTP is great. It powers websites and APIs, and it's built to be very descriptive and very flexible. And it can be used for IoT connections, but it's not lightweight and it's not terribly fast. The problem with HTTP from our device's point of view is that it's pull only. So we have to constantly connect and ask, are there any updates? How about now? How about now? Which is really data and time consuming. And on low power IoT devices, we don't have much memory, we don't have much power, and we don't have much bandwidth. So we need protocols that are designed to be small and fast. And this is where MQTT comes in. Message queuing telemetry transport is a connectivity protocol which was designed to be incredibly lightweight. Connecting to a server takes only about 80 bytes and the device stays connected the entire time, so we don't need to keep reconnecting. Data is published when it's pushed from the device to the server, and the device subscribes to the data published from the server itself. Because the size of the data that's being sent over MQTT is small by design, messages can be sent quickly, making the hardware very responsive, making it feasible to change the lights on the t-shirt in actual real time. And with MQTT, which is a great fit for our hardware, what we're going to need is an MQTT broker. And the broker is the server that the devices connect to in order to use the MQTT protocol to listen for messages. The broker keeps track of all the clients that are connected and the topics that they're subscribed to and forwards any messages to any subscribers. So in this case, I'm using mqtt.ably.io as my broker, which is just a third party that your IoT things, your IO things can connect to in order to receive messages. The cool thing about the Ably broker is that any messages we send in our browser to an Ably channel using the JavaScript SDK are also sent out over MQTT automatically. And using the Adafruit Feather Huzzah with the Arduino IDE is nice and straightforward. There's a walkthrough of getting it all set up under this link here. And writing the code for the board, the first thing that we need to do is include this Wi-Fi client secure here, which lets us connect to Wi-Fi, and then include MQTT, which lets us use MQTT. We set up a config for the board because it makes keeping track of our credentials easier. So we need things like my Wi-Fi SSID and password, then the name of the broker itself and the port it's going to be using, the username and password that I will need for that, which is just going to be my API key. And then that scary looking blob of hex that you can see there is the fingerprint of the SSL certificate for Ably's MQTT Broker, so https mqtt.ably.io. And we need this so that the Wi-Fi client secure can verify with the SSL certificate that it sees when it opens the connection. So if you don't provide this fingerprint, a connection over HTTPS will fail. And then finally, we've got the channel name set up here. So similar to what we did for the web app, we need the Feather Hussar to connect to the Ably MQTT server and then to subscribe to a channel. So first we create instances of the Wi-Fi secure client and the MQTT client. Once we've connected to Wi-Fi, the secure client lets MQTT use SSL to connect to our Ably channel using the credentials that we had from the config. So that's what's happening here. We're connecting, we're sending it all those credentials, and once we're connected, we are then subscribing. So let's say that we received the message that we sent earlier, so 001 and purple. We can split it at the hash character into 2 separate strings. We're then going to convert the hex into RGB and send the pixel number and the RGB values to the lights to update, which is what is happening here in this code. Now, the eagle-eyed amongst you may have spotted a little mistake, or perhaps something that I didn't quite consider when I wired up the lights. So let's take another look at the squares from the web app. Now, I gave each of these squares a number to represent the number of pixels in my LED array, like so. And when we read, we go from left to right. This is how enumeration of arrays work, but this isn't how I soldered my lights together, if you remember. I wanted to keep my wires nice and neat, so I soldered these little jumps at the end of each one. Not only that, I connected the cable up to the wrong end of the first strip. So if I was to represent these LEDs with our pixels, my array now looks more like this. 16, 15, 14, 13, and so on, which isn't exactly the way that I numbered the LEDs in my SVG. And I have affectionately termed this method of enumeration snake mode, which means that I have to essentially reverse every other line of the array. So on the board, I've got a method which checks whether the position needs to be reversed. So here we've got the X and the Y values, which is the X and the Y, to work out where the pixels should actually go. So to calculate which row the pixel is on, first of all, we divide the pixel number by 16 and then modulo 2 to work out whether or not we're on an odd or an even row. And then we can work out how many pixels came in on the rows before. So say we're on row 3, we want to get how many pixels are on these 2 rows here. Then if it's an odd row, we minus the X position from 15 to get its reversed position, add that to the chunk of pixels that came before, and we have the new pixel number. So now we have an app which can send a message, we have a board which can receive it and process it correctly, and we have a display that can show it. So we say a little prayer to the demo gods who seem to have been smiling on us so far today, and I'm going to stop sharing my screen and make this full screen so you can all see your own handiwork. Let's bring it a little closer if we can. I think someone's going to have to start adding some black in, otherwise it's just massively oversaturated. Yeah, oh. Hooray. Let's put you back up here. And I'm going to share my screen again for my final slide. So I hope that you've enjoyed this talk and that it has slightly demystified IoT and hardware for you, and that it encourages you to give it a try. My code is all on GitHub there. I will share the link to the slides in the Discord and on Twitter. And thank you all so much for listening.